Okay, so this is for, the electric field distinction, and I have 4 particles, 2 which are negative, or 3 which are negative, and then 1 which is positive. With the measurement, I'm going to be measuring the electric fields from the center of the square, and the square's sides have 50 millimeters, so that's, equal, because it's a square. And so what it's asking me to do is find the electric field for the x component, and then find the electric field for the y component. So what I'm first going to do is look at the charges to determine what my electric field is going to be. So negative has the electric fields pointing toward the charge. So I'm going to draw that. And then once again, a negative charge. So it's going to be pointing towards this charge. And then, I forgot to mention that all of the particles have the same charge of 4.0 nanocoulombs. But obviously these ones are negative. Okay. And then the positive, it points away from the charge. So these are all equal in magnitude. And so it's going to be pointing towards that corner as well. And so these 2 charges are going to cancel out, leaving me with these. So I'm going to set up to where, okay, so my video shut off, and hopefully I'll figure out how to combine them. But as I was saying, so I need to find the x component and the y component. And so first what I'm going to do is, I've already drawn my vectors according to positive and negative charge, but what I need to do is associate, because this will be cosine and this will be sine. I need to figure out what the angle is. So, hopefully it's in there. So this angle right here. So as you can see, the vector is going through the middle of what would be a 90-degree angle, and half of that would be 45 degrees. And so with that, we can figure out what the sides are going to be as well, or are anyways. So if we take theta, which is equal to, it's going to be tan, and then we're going to take, so each side, let's say, is A, so 50 millimeters is equal to A, so that would mean that because it's in half, it's going to be A squared, and then, it's a triangle, so A squared. We're going to take the inverse of that because we want to find R, and we know that tan, so we know that tan theta is equal to theta is, oh my goodness, theta is equal to 45, and so we can do R, so taking the Pythagorean theorem into account, hopefully I'm showing, okay, A squared, that's going to be squared, A over 2, it's going to be squared, and then that is going to be square rooted because you have a triangle. over here. This is your triangle. And so a squared and a squared. I don't want to overcrowd it. Hopefully you can see that. Oh, wait. No, a squared plus a squared. Okay. And then this would be a squared. Okay. Or I keep saying squared. Over 2, sorry. A over 2 because it's been divided. You know, this was a, and we divided it into this little section. So we divided it in half, essentially. Okay. So, square root of that. So what we're going to be left with is a, I think it's square root 2, but I could be wrong. Because, yeah, it's 2 plus 2. Yeah. Okay. So, we have r now, which is right here. This is r. R is up there. It's getting really crowded. Anyways, so now we can take E equation, and we know it's K, Q squared in this case because the charge is the same. So it's going to be 2 of that, or I can just 2Q. Let's say 2Q. And then it's going to be over R squared. So we just derived that, which was A divided by square root 2, which is going to be squared. So I already claimed that A is 50 millimeters, so we need to make it into meters. So, okay, let's plug that in. So, because we're trying to find E so that we can take the cosine 45 of it. So, anyways, we're going to do 9.0 times 10 to the 9th newtons meters square over coulombs squared. That's K. And then we're going to do 2 of the 4, it's nano, so 4 times 10 to the negative 9 coulombs. And then we're going to divide that by 0.05 meters. And then square root 2. And then 2. I'm going to need my calculator. Sorry about this. Okay. Hold on. Let me calculate. Times 2 times 4 times 10 to the negative 9. And then we're going to divide that. Square root 2. Okay. And so what I end up getting is, hopefully I'm right, 5,700 and, oh my gosh, 57,600. I have that all. Okay. And then, so meter squared canceled out. And then one of your coulombs canceled out, leaving you with newtons, well, and this one's canceled out, newtons per coulomb, which is what electric field SI unit is. So that means we did it right, right? Okay, so now we want to take the x component. So we're going to do E of x. I'm just going to take from the center. Okay, and then we know that to be E cosine 45 degrees, because we figured that out earlier, right there. Okay, so then we now can plug in E. So let me do that. I'm just gonna just calculate that times cosine because we're taking the x component. So what I get plugging in E is 40,729 Newton coulombs. Okay. And then we're going to go down here. And so we're assuming that the electric field is going to be uniform because it didn't say otherwise, right? So then I can take this and plug in my 57,600 Newton coulombs. And so because it's the y, we're going to take sine 45 degrees, which should be the same. Let me make sure I'm remembering correctly, though. Cosine 45. Yes, it's the same. And so we get that to be Newton coulombs. And so with that, we have the answer. The x component and y component end up being the same thing because it's uniform electric fields, right? So that makes sense. And yeah, so this is a distinction for electric fields using more than one charge. So electric ELEC.02, and there is my answer. Okay.